Okay. Yeah. Now it's working. Okay, so let me start with an introduction. The morning session was about these geometric, random geometries, basically. And the idea is to take this hard problem of the integer quantum Hall transition and try to formulate it in terms of this of random geometry, in order to have a tool that is alternative to conformal field theory, which is usually attempted to apply conformal field theory to the integer quantum Hall transition. This seems to lead to results which are controversial. It's not really clear what is the conformal field theory, and the result is that we don't really know the critical behavior of the integer quantum Hall transition using the usual field theory methods. And the idea is to take this problem and map it to a problem which is related to random geometries. It's these random curves that appeared in all the talks basically this morning, and see whether it's possible to apply these types of methods to make some progress there and hopefully get the critical exponents of this transition. So I'll start with just an introduction of how we can use random geometries, fractal dimensions, all these concepts in order to understand critical behaviors of a system. This is a kind of a basic thing, a very old concept that relates the fractal dimensions of fractal sets to critical dimensions in the usual sense of physics. So in statistical mechanics, let's take a two-dimensional system at criticality. It has scale invariance, etc. We see all sorts of fractals in the plane, the ones we saw all this morning. For example, in percolation, we have these green and white sites that are chosen at random at some probability, such that at a certain critical probability, we get a percolating cluster throughout the system. And when we take the system, we change the probability of green versus white cells, the system goes off criticality, which means that for a large system, we won't see a spanning cluster from one side to the other. So for example, the experimentalists may connect leads to the two sides, and there may be a current flowing only if there's a percolating cluster. But if we take the probability out of criticality, then for a large enough system, it will be disconnected, right? And we want to understand what is a critical exponent. Namely, if I take change the probability of green versus white a certain amount, small amount, how big is a system that I would need in order to start seeing that I don't get spanning clusters. If the system is too small, then I don't see the fact that I've changed a few sites. But if the system is large enough, I do see it. And this defines a critical exponent, because the size of the system as a function of the deviation from criticality will be a critical exponent that one can measure in the lab, right? And for percolation, this is related to the fractal dimension of a certain set within this percolation system. If I change one of these sites from green to white, then I will cut the system into two. Only if I hit one of these cells, which are called red cells or cut points, in which if I remove it, then it will cut the connectivity from one side to the other. And I can identify a set of points on this cluster which have this property. For example, this red point, maybe this is such a point. And these points have a fractal dimension. So the number of, which means that if I take a system of size L and the lattice spacing is epsilon, then there's some fractal dimension D of these red points. And the number of red nodes that I will see will be this size of the system to this fractal dimension. Right? So the probability of a point to be red is this number divided by the total number of cells in the system, which is this thing. And now, intuitively, it's clear that this probability of a cell to be red, to disconnect the cluster, is related to this critical exponent of that we measure in physics. And of course, the way to relate it is simple. The probability that I disconnect the system is the deviation from the critical probability of green versus white times the probability that the cell is red. And this has to be order 1 in order for the system to be just the right size, in order for this to be a critical, what's called the length, the correlation length, right? So this says that the amount of deviation I would need from the critical one in order to get to disconnect is some power. Yes. So the size of the system is some power of this deviation. So this is the critical exponent, and this is a fractal dimension. This is an example of relation between them. So the idea is that to apply this simple logic, so this, yeah. So if I drew all the red points, it would be a fractal set. Sorry? Yeah, and they have some fractal dimensions. So if I do box counting for this set, yeah. Okay, so this is the idea how to connect these two concepts of fractal, which is very old, of course, but I just wanted to remind that to connect these two, the connection between the physics approach and the more mathematical approach, looking at fractal sets and studying their fractal dimensions. And the system we'd like to apply this to is the integer quantum Hall transition. And of course, the problem is already in the title of this system. It's quantum. So it's not clear why we should be able to look at fractal sets, at classical fractal sets like we saw right now, and be able to say something about the transition, since it's quantum, right? It's not described by classical clusters. So this will be the subject of the first part of the talk, which I will focus on that, why we could at all think of the integer quantum Hall transition in terms of classical clusters, fractal clusters. And the next part of the talk will be developing these ideas some more in order to see how we can indeed describe these clusters more specifically. Okay, so I'll give a description of what is the integer quantum Hall transition. I'll give it more in a, so I assume that the physicists kind of know this, so I'll give a more mathematically oriented description. Namely, I'll describe I think about the integer quantum Hall transition as something described by the Chalker-Coddington network, which is some sort of lattice model. Right, we physicists think about the integer quantum Hall transition as a transition in which we have puddles of electrons. These are the gray areas, and the electrons can move along these puddles in a sense prescribed by the magnetic field. So the electron can go on one puddle, but then the electron can jump to the other puddle in the node that connects them. But and the idea is that in reality these links are really associated with actual methods which are convoluted and have different lengths. And this is modeled in this description, in the Chalker-Coddington description, as the fact that every time an electron traverses a link, it picks up a random phase, which is quenched. So every time the electron goes from here to here, it picks up a random phase. And every time an electron gets to one of these links, it can either turn right or left. It can either scatter right or left. And it can come to a link, a vertex from here or here. There's a 2x2 matrix which describes the scattering event of an electron either coming from here to here and leaving to either ends. So this is so each node here acts as a beam splitter with this scattering matrix, right? And the rules of the game is that we want to compute the probability or the conductance from A to B. The probability to, if I put an electron in A, that it leaves through B, this network. And this is given by the following something that we term the green function, which is the square root of this probability. So this is GAB. So GAB is the probability amplitude of going from A to B. And to do that, we sum over all the paths that go from A to B. And for each path that I draw, I take for each path that I draw, I take all the links that the electron traversed in order to go from A to B. and multiply out the random phases that are associated with each one of the links. So this is the first factor. So just this, the Green's function is sum over all paths, and then there's a multiplication of all the links in the random phases. So this theta L is a random variable from 0 to 2 pi on each one of the links. And then each move from L to L prime, so L and L prime are two links adjacent on the path. We take a matrix element of this matrix, which corresponds to the particular path, the particular way that the electron traversed the link. So, for example, if the electron came from 1 and left through 1 prime, I'll take this element from 1 to 2 prime. I'll take this element. If it came from 2 to 1 prime, this element, etc. Right? And yeah, it has to be a unitary matrix. So this is a beam splitter, right? The determinant is 1. 1 plus 1 is 2. 2 divided by 2, and there's a square root of 2. Yeah. So this is a unitary matrix. Okay, so that's the rules of the game in terms of the Chaucer-Coddington network. And what we see is basically that what we want to compute is not the Green's function, but the absolute value squared of this Green function, and average over the disorder. Right? So we take to do that, we take this Green function, which was a sum over all paths, and square it, which means that we take pairs of paths, and then we take the weight, which is this expression that we associate with the path, times a complex conjugate one associated with the path p prime, and average over these phases theta. Right? And the first thing one notices is that if we take two paths and we do this, unless these phases cancel between the two paths, namely unless they traverse the same number of links, the same number of time, then we will get 0. Right? So this means that if a path and a path prime are to interfere, to contribute to this double sum, then they have to be similar to this situation. Namely, two paths either are the same, or they traverse the same links, the same number of times, but at a different order, this is an example of that. So this is an example of an interference of two paths. This is quantum interference between two different paths, and even though they traverse the same links, they traverse it in a different order, which means that I should take into account their interference. So, and basically what we can do is organize these double sum over pairs of paths as a sum over pictures, in which I don't say in which order the links were traversed. And then after I know what picture I'm talking about, I can try to find out all the different paths that correspond to it, and then sum over that, right? And these will interfere positively. So this is a way to say that. So this object, the conductance, is a sum over all pictures, and there's a factor of 1 over 2 to the power L, which comes from this 1 over square root squared. This is not very interesting. 2 to the power L. And then this thing has nothing else but plus and minus 1s. This factor has plus and minus 1. The phases cancel, plus and minus 1. So each one of these paths, I associate a sign, which is the number of turns which correspond to minus, which are these downward-looking turns. So I sum over this. So every such picture gets an amplitude, which is a sum over all these paths. Each path is just a sign, which is just taken from this matrix. And the point is that I square that, right? So I have a weight for every picture, which is positive. And this puts this system in the class of statistical mechanics systems. I have a positive weight for a cluster. This I can think of as a cluster, a positive weight. And the weight is very similar to a random walk. This would be the random walk weight if this would be just the number of paths that correspond to a picture. But this is not the number of paths. It's something squared, which includes interference. Okay, so what can we learn from that? let's see. So let's draw one of these clusters, a huge cluster in the Chakra-Coddington network. And it's known by work by Lawler and others that two properties of this cluster are enough to define its statistics uniquely, with some caveat, which I'll explain in a moment. So first of all, the two properties that completely define the weight of this cluster, or the shape of this cluster, is that first of all that the weight is intrinsic. I can look at this cluster and say immediately what its statistical weight is without knowing the shape of the system it's living in. So this means that the weight of the cluster is intrinsic. In other models, that's not true. If this were an Ising model cluster, then it would care about the shape of the overall system. So this is the first property. And the second property is conformal invariance. This is a critical system, so it has scale invariance. And by usual assumption, it is promoted to conformal invariance. So the system is conformally invariant. So these two together tell us that this shape of the system is completely defined, but not exactly, only the external perimeter. So the external perimeter of this system is completely defined. So a lot is known about this external perimeter, and everything can be computed. Basically, the fractal dimension of this thing, probabilities of fjords, every object that you can think of can and actually probably has been computed already. So this sounds like a powerful tool, but there's a problem. There's some bug in this way of thinking, is that it's a bit too general. So a lot of statistical systems, quantum and classical, have this property of conformal invariance and intrinsic weights. So percolation, for example, has this property. It's basically C equals 0. So percolation, random walks, the integer quantum Hall transition, other Anderson transition, etc., all have this property. So this means that this approach, all this information that can be taken from this picture, is actually shared by many models, and we know that they are in different universality classes. Percolation behaves very differently than the integer quantum Hall transition, etc. So whatever we can learn from this approach at this point is limited, because it cannot tell these systems apart. And okay, so I'll skip this recap. And the question is, what can we do in order to improve the situation? And basically, let me just say that the idea is that we have to look further into within the cluster. So it's clear that the information about the transition, the critical exponents, have to lie within this cluster, of which we know only at this point the outer boundary, right? So what is the approach that we may take in order to study its internal structure? So of course, as usual, we can take the conformal field theory approach, but we want to use something else. So let's look a bit more generally. What do we do in order to solve a critical system in 2D? So here's the critical system in 2D, the Ising model. All the up spins are gray, the white spins are down. And here are all the clusters at criticality. There's one huge cluster for some reason here, maybe boundary conditions. And there are many, many smaller clusters. And there are two ways to look at the system. And one way to look at the system is to think about local correlation functions. Right? So local correlation functions is like, what is the spin-spin correlation function from here to here, etc. All sorts of local objects. And conformal field theory is very well suited to do that. So in conformal field theory, we have these local operators as fields, and we know how to compute their correlation functions. But we can also ask questions about stuff like the fractal dimensions of this curve, all sorts of other fractal sets that are hiding in here. And this can be attacked with conformal field theory using quantum gravity, all sorts of tricks, which are quite complicated. But recently, and as we heard from previous talks, there's also the method which is related to the Schramm-Loevner evolution, or a conformal loop ensemble, which is something done by Scott Sheffield, that allows us to deal directly with the with the clusters themselves, to describe the statistics of these clusters directly without going through conformal field theory, right? And the idea is, as I've mentioned in the beginning, is to think about the integer quantum Hall transition within this approach, and specifically trying to find out what's lying inside this huge cluster, taking that approach. Okay, so how do we describe the inner workings of this huge cluster, of which we only know by now the external parameter, the statistics of the external parameter? So this includes a series of mappings and some concepts from probability theory that will allow us to understand better how to map the system, or how to map the interior of this cluster into a set of loops, fluctuating loops, which we hope can be described by methods which are related to to SLE and other things. But some of it is work in progress, and I will be able only able to show how this program works up to some point. Okay, so the first thing we do is we started off with the Chalker-Coddington model, or the gray lines here. The electron can go in a certain sense. There are little arrows here that you barely see. And we can think about the median lattice, which is a lattice whose vertices are the midpoints of the Chalker-Coddington model. And then there are arrows on this lattice, because if I'm going here as an electron, starting from this vertex, I can jump only to that vertex. Namely, there's only one direction I can move. Right? So the electron can move from here to here, namely from this link to that link. And what we get is a Manhattan lattice. And the nice thing about this representation is that it's easy to keep track of the sign that I've mentioned before. The sign is just the red links on the Manhattan lattice, is minus on the red links on the Manhattan lattice, and plus on the black links. So the Chalker-Coddington model can equivalently be thought of an electron moving on the Manhattan lattice by just thinking about which links the electron passed through on the original lattice as vertices being visited on the Manhattan lattice. Okay, so, but we still need to count all the way we traverse this Manhattan lattice. So an electron takes some path on this Manhattan lattice, picks up sign, which is very obvious here because it's the red links, and we still have to keep track of that. And the way that we may keep track of paths is we make use of some ideas from probability theory, which relates these paths to trees. Okay, so there's a mapping, a many-to-one mapping, many-to-one, between the paths. For example, this is a path, and this can be mapped onto a tree. And the way one does that is the path, for example, visits some vertices here. It visits the same vertices on this tree. But for every vertex the path visits, we only draw on the tree the link that led to the first visit on this site. For example, this site is visited twice, the first time here and the second time from here, but the tree will only contain the first visit. And the same for other points. So this gives us a tree related to a path. Right? And now we can keep track of the paths by counting trees rather than paths. And this is the way we have to do it is a bit more complicated than usual. It turns out that if you take this uniform measure on paths, you get a uniform measure of trees or something. But we will actually have to keep track of the number of times we pass through each link. So this is a bit more complicated than the usual way it's applied, but it's still a useful mapping from paths to trees. And we heard about trees earlier today as well. And and how do we keep track of trees, right? So there's another mapping. So it turns out that one has to apply another mapping, which is done by Temperley, that maps the problem of counting trees to counting dimers. And the problem of counting dimers is familiar for us in physics. It's related to fermionic free fermion models, which can be bosonized into free boson models. And in terms of mathematics, it was shown by Castellin, which basically formulated the problem of counting dimers in terms of counting of some determinant of some matrix, which actually gives it it puts it in the universality class of fermions. Okay, so what is this mapping? So let me just go through more or less the idea behind this mapping. So we start with the Manhattan lattice, and we have to move to another lattice again in order to count the dimers. Okay, so the idea is that every arrow on the Manhattan lattice is doubled, and what's called the temporally, see double arrows, and what's called the temporally lattice is one in which only the second half of the arrow is retained, and the first half of the arrow is erased. So here, see the second part. For example, this is the second part of the arrow, and only that is retained. And this is the second part, only that is retained. The first part is erased. But in addition to that, a vertex is put in each middle of each of these plaquettes. And from it, there are lines going, or links going to each one of the midpoints of the vertices adjacent to it, around it. So, So after doing this transformation, which I just briefly showed to explain that it's actually something well-defined that one can easily create from the Manhattan lattice, one obtains this lattice. Okay, so this is a lattice. And on this lattice, if we count the number of dimers, we basically count the number of trees. So how do we count dimers? This is due to Castellin, or in physics, it's a well-known subject, how to count dimers on some lattice. And the idea is that you have some matrix K, whose indices, the I and J indices, enumerate the vertices on the lattice, and every element is 2 points on the lattice, I and J, and if they're linked by a link, then they get a number. The matrix element is a number which is assigned in this way. The numbers are 1, -1, and I. So there are certain well-defined procedure to assign numbers on these links in the matrix, such that the number of trees on this lattice is basically the determinant of this matrix. And it's more general. Basically, if I want to find what's the probability of a certain link to be populated with a dimer of the correlation function, it's such a determinant of the inverse of K, which means basically that we have a fermionic problem with a green function, which is just the inverse of K. So you invert this matrix K, that's a green function of some determinable problem whose answer all determinant, a fermionic model. Okay, so how do we, what's the model basically that we're talking about? So it goes like this. So we have these paths that go through the system, and we draw a loop of all the vertices visited once, at least once, a loop of all the vertices visit at least twice, 3 times, etc. And for each one of these loops, we count all the trees, all the paths, which is equivalent to counting all the trees, which is equivalent to counting all the dimers, which is equivalent to computing this determinant. So each one of these loops has a weight, partition function, which is a determinant of a matrix that one can easily write. The loops? No, they don't pass through all points. Yeah, there's a 0 loop. So this is 0, this is 1, 2, 3. So for example, if you look, oops. That's far. Okay, so this is 0, 1, and this will be, for example, 2. Okay. Yeah, so using this method, we can basically have some sort of a loop model for which so we had this shape, these loops, and each loop is populated by these trees. So, for example, for the one loop, there is some sort of a lattice that is all the points on the one loop, and we have to count all the dimers on this lattice in this very strange temporally lattice associated with the Manhattan lattice. And we have to weigh the loop correctly, so we have to take account of the sign, which actually means each dimer that lives on a magenta link has a minus sign, and we have to include that in the matrix K, which is a simple procedure. And let's think briefly about what kind of... so basically what we have here is this loop model. And so the idea is that we have loops, and each loop is populated with the matter field. That's a physics way to say it. Or another way to say it is there's a partition function associated with this loop, which is given by some CFT partition function associated with the particular dimers that are living within sites. And we can ask how to understand this partition function better. So the partition function of dimers is this determinant of the Laplacian square, basically. This matrix K is basically related to the Laplacian. It's actually the derivative or Dirac operator, but the partition function of the dimers turns out to be this. But we have to reweigh that with the taking into account the minus signs. So the matrix that we're using is not directly the usual dimer matrix, but the one that includes the sign. And there's a certain constraint that I haven't mentioned. So we can't just draw all the possible trees. We have to keep into account the fact that each link, each vertex is entered and exited the same number of times. So this is a certain constraint on these trees. And what we'll see is that there's a way to include both the sign and the constraint within a description, which in the end turns out to give us what are the matter fields which lives within each one, through which we want to eventually describe the system using some sort of a loop ensemble, which will hopefully allow us to obtain a loop ensemble, a description of the fractal dimensions of all these subsets of the system. Okay, so the way to do that is to use Booleanization to include the constraint and this and the sign. So those special features of the constraint and the sign that makes the system basically the quantum system can be introduced by thinking about a height function. So there's a way to describe this dimer through a height function, a function that whose value jumps by pi or something every time we go through a dimer. And and thinking about the height function, which is phi, one can equivalently count dimers. And the partition function, or the weight of the statistical weight of this height function, is given by phi k dagger k, where k was this Castellan matrix. And the point is that at the limit, k goes to 0, it's small k's. So this matrix is defined everywhere on the lattice. But of course, there's a translation invariance, so we can do Fourier transform and write it through k, the wave number k. So when you look at this matrix k dagger k, which includes all these signs, the sign, one can see that there are many what's called massive modes. When k goes to 0, eigenvalues that when k goes to 0 go to a constant. They are irrelevant, of course, because in the critical system they're not important. And there are many of these modes, not many, 3 modes, sorry, that go to k squared. These are the propagating modes that we have to keep account of. So in the end, what we end up with is a system in which we only retain these propagating modes through this matrix A. So I truncate the matrix k dagger k into a smaller matrix A, which only includes the propagating modes. We have a height function for each one of these layers, 1, 2, 3, etc. So we have a vector height function phi, which depends on how many layers I have at a point. And then there's a constraint, and luckily, the constraint which says that the number of times I visit a vertex and the number of times I leave a vertex are equal can be written in this way through the height function, which means that this problem is tractable. So this kind of partition function is tractable. Oh, V is I have to write it down explicitly, but it's a certain, I have to take the constraint and expand it in these eigenvectors, which are, I can write it, but I didn't. Okay, it's some well-defined object that can be written. Yes. Yeah, but this will be it has a good conditional limit as well. Yeah, so this can be exponentiated, and the function can be written. One can identify in principle. We haven't completed this program, but one can identify in principle what kind of conformal field theory, what kind of matter fields live within each one of the loops. And this is supposed to provide us with some sort of a description, a loop model description for the system, and hopefully one can apply methods, which were some of them discussed earlier, to obtain fractal dimension of certain sets, and hopefully one of the sets will be one should identify a set which corresponds to taking the system off criticality, much like in percolation, and that would allow to compute the critical exponents system. So yeah. So yeah, that was my conclusion, and I think I'm done. Early. Yeah. Okay. Yeah. We can also eat. Yeah.